Okay, so in the second part of this lecture on the matrix formulation of the linear model, I'm going to introduce two interesting ideas. One is the likelihood ratio test, and the other is the analysis of variance, or ANOVA. Okay, so in the likelihood ratio test, we're going to define the likelihood ratio statistic as the following. We are going to compute the likelihood under a particular parameter value and compare that to the likelihood under some alternative parameter value, right? So if you remember what is the likelihood, I just want to remind you quickly about what we are talking about. So let's see here. So if you remember, d norm is a function in R that allows us to compute the likelihood, right? So suppose I have my data. Let's say that my data that I've observed is the number 10, okay, or let's say 500. Okay, so now I can compute the likelihood function for the mu parameter in the normal distribution, right, for different values of mu. For example, let's say that I decide that mu can have values going from 300 to 700 and I create a sequence by 0.01, right? So now I can use the d norm function. Given my data x, right, which is the data point 500, I can compute the likelihood function for different possible values of mu. Okay, so let's take a look at that. Mu and no, sorry, what do I want to do here? Yeah, so let me assume that standard deviation is 100 just for convenience. I'm just choosing this number, and so I've got my likelihoods that I can compute now, and I can plot this likelihood against different values of mu, right? So I can see how the likelihood changes given the data for different plausible values of mu. Okay, so let me plot this. When I do this, make this plot, what I notice is that the maximum value is at 500. The maximum value of this likelihood function is at 500, right? So 500 is the maximum likelihood estimate of the mu parameter, right? We have only one data point in this example, so the mean of this data point is the number itself, right? So that's what I had explained to you some lectures ago, that the sample mean is the maximum likelihood estimate given the data that we have. So that's just to remind you what the likelihood is. So now the likelihood ratio test that I'm talking about right now, this likelihood ratio test, this looks, whoops a daisy, what happened here? Yeah, so this likelihood ratio test looks very difficult, maybe, I don't know, but if you think about it in practical terms, what it actually is saying is that we want to know which value of mu is more likely. Okay, so let's say I can compute the likelihood of under a null model where I assume that the true mu that generated that data point 500 is the data I've generated, right? I have a hypothesis that the true mu is 0. Okay, so I generate the likelihood under the true mu, and then I generate the likelihood under an alternative model which I'll call M1, which takes the mean of x, which is 500. Notice that it's just one data point, so the mean is 500. I can compute the likelihood under that value as well. So really the likelihood ratio test is computing the likelihood under two different assumptions. Okay, so what you can see when I compare these two likelihoods intuitively is that the likelihood under mu being the mean of x is higher than the likelihood under the model where mu is assumed to be 0, right? That's a very small number there. So really the likelihood ratio test takes the ratio of these two and uses that statistic to quantify the extent to which there is support or there is evidence for one or the other model. Okay, all right. So that's what this this complicated looking statement is saying. Under some null model, right, what's the likelihood, and under some alternative model, what's the likelihood. Okay, so as an example, imagine that we have independent data points x1 to xn. They're all coming from the same normal distribution with some unknown mean and standard deviation. So let's just assume that sigma is known, just to make our life easier in this discussion, right? So we are only going to talk about mu here. So let the null hypothesis be, right, that the true mu is mu sub 0, some value mu sub 0, could be 0 or something like that, right? So the alternative hypothesis is going to be that the true mu is not mu sub 0, right? So we are now going to use the likelihood ratio test to do this kind of hypothesis test. Okay, so in the likelihood ratio test definition, the numerator is the likelihood under the null model, right? So what is the null model? The null model states that the true mu is mu sub 0. That's this number here, right? So what I have written down here is the likelihood, the d-norm function. This is the d-norm function actually. Given some data, some vector of data points, right, and given some hypothesized mean and standard deviation sigma, I can now compute the likelihood for all the data that I have, x1 to xn data points, right? So that's really what I've done here, right? This is just a PDF of the normal distribution that I've written out here. Okay, now that's the numerator of the likelihood ratio test. Now I'm going to focus on the denominator of the likelihood ratio test. The denominator, for the denominator, we're going to choose the maximum likelihood estimate, right, by taking the sample mean x bar as our alternative model. Okay, so that's the alternative model that I'm considering now. So this is the denominator now of the likelihood ratio test, right? All that has changed is that instead of mu sub 0, I'm using x bar. Okay, everything else is the same. So now if I literally compute the likelihood ratio statistic, what I get is these two terms. These are both PDFs, probability density functions of the normal distribution, under two different assumptions. The numerator is making the assumption that the true mu is mu sub 0, and the denominator is making the assumption that the true mu is the x bar sample mean. Okay, that's the only difference. So now we're going to solve this complicated looking equation. But the first thing to notice is that these terms are going to cancel out. Okay, so that already simplifies the equation, and that's what I've done here, right? We cancel out the common terms. Now we just have to solve this equation. Now this equation is actually a ratio of two exponents, right? So exponents, I'll call the numerator, this whole thing, I'll call it A, and the denominator I'll call B. So I mean, this complicated thing really reduces to this kind of term here, right? So this kind of term we know how to simplify. Instead of talking about the likelihood ratio, we can talk about the log of that likelihood ratio, right? So we can just take the log of this, right? When we do that, any exponential will cancel out if I take the log, right? So what's going to happen is that I'll get A over B, right? So but so sorry, this is not what I want to say. So what I'm going to get here is A minus B, right? A minus B, because this is a ratio here, and in the log scale the ratio becomes a subtraction, right? So that's how I end up with the numerator turning up here, and it's subtracted by the denominator, these terms here, without the exponents. Now these two are gone now because I took the log of everything. Okay, so now I have these subtractions. Let me just erase all this. This looks messy. Right. Okay, so I have these two terms now, and these actually will simplify a lot because I have a common term. This is a common term in both these terms. So I take that term out, and I'm left with this complicated looking expression here. Okay. Now, what do I do with this expression? Well, one thing to notice is that this expression here can be rewritten in a very interesting way. This is a very interesting trick in statistics. You will see this many times in the literature if you read textbooks on stats. If you have an expression like the sum of x sub I minus mu 0 squared, you can rewrite it in terms of the sum of two expressions as shown over here. I won't derive this, but this is just a consequence of simple algebraic manipulation. Okay, and you don't need to stress over trying to do it yourself. You can take it on trust. It does work, right? So I can rewrite this term as this longer expression here. This is interesting because the second term here, let me erase some of this again. What you're going to notice now is that this second term here is going to match exactly this term here. So these two guys will cancel out, leaving us with n x bar minus mu squared, right? So that's what's going to happen next, because I will rewrite the left hand side in terms of this summation, and that will leave me only with this term here, because this guy will this term is going to cancel out with this term. These are two identical terms, right? So they will cancel out, leaving us with this term here, right? So that's how I end up with this long complicated term simplifying to this one here. That's a very neat result, because now I can talk about the log likelihood, which I'm writing as this expression L, in terms of the simplified term minus x bar minus mu squared, mu 0 squared, and then this common term minus 2 negative 1 over 2 times sigma squared as a constant here. Okay, so now given this expression, I can rearrange the terms by multiplying both sides by minus 2 times the log likelihood, and what I get is this very interesting looking term here, right? If you look at this carefully, this should actually remind you of the t-test. Remember that the t-test, when I wrote down the observed t value, it was x bar minus mu 0 over the standard error. But what is the standard error? The standard error is x bar minus mu 0 over sigma standard deviation divided by the square root of n, right? So really what you're seeing here is a square of this term. What you're seeing is x bar minus mu squared divided by sigma squared and then multiplied with n, which is the same thing as, oh sorry, I just wanted to erase this. So erase this. What I wanted to say is that I could write sigma squared over n here, or I could write x bar minus mu 0 squared over sigma squared multiplied with n, right? It's a division here, goes up and becomes a term here. So this is exactly what we've got here, right? This is exactly what we've got here. We've got something that looks a lot like the t-test, except it's the square of that, right? And that is negative 2 times the log likelihood ratio, right, between the two models that we are considering. Right, so this should remind you of the t-test. That's what I was trying to show you here. Basically what this test is doing is that it's getting a statistic that represents how far away the sample mean is from the hypothesized mean. You remember the t-test? That's exactly the same test that we are doing again. It's a distance test, you know. Okay, so the likelihood ratio test actually simplifies to a very intuitive thing, which is very similar to the t-test that we had learned earlier. Okay, so in general we will define the likelihood ratio test statistic as follows here. Okay, so what I will do now is that I will use lambda with theta in parentheses to represent a particular model. So if I have a model with some particular parameterization, like my null hypothesis, for example, I will write that as lambda mu 0, right? And if I have another likelihood, oh, this was a mistake, it should have been written as Greek lambda, right? If I have another model with some other value other than the null hypothesis mean, I will write lambda theta 1, right? So I take the ratio of those two guys, and -2 times that value is going to give me the likelihood ratio test statistic. Okay, so as I just showed you earlier. And so because we're talking about log likelihoods here, we are going to take a difference in the likelihoods instead of the ratio, right? So the ratio refers to the likelihood. The log likelihood will do a subtraction then, because on the log scale every ratio becomes a subtraction. Okay, so right, so basically the interesting thing here is that this log likelihood, right, so the ratio that I'm calling the likelihood ratio is going to be as the sample size approaches infinity, as the sample size goes up, this difference in log likelihoods, or the log likelihood difference in log likelihoods, is going to approach a chi-squared distribution, which is a particular distribution that is defined by something called the degrees of freedom. The degrees of freedom in this case refers to the difference in the number of parameters between the two models. So if I have a null model where I have one parameter less than the other model, right? So let's say I say that my null hypothesis is that mu is 0, right? I have one parameter less, but in my alternative model I have one extra parameter. The difference in the degrees of the degrees of freedom in my chi-squared statistic will be 1, because there is a difference of 1 between the two models in terms of the number of parameters there. So basically the log likelihood difference that we will calculate, this thing here, right, this will be compared to the chi-squared statistic with a particular degrees of freedom, and we will use the same logic as the t-test to figure out whether to reject the null or not. If our the difference in log likelihoods is very large, right, relative to some criterion, then we will reject the null hypothesis. Okay, so this what I've just shown you here, this fact here, that the difference in log likelihoods approaches the chi-squared distribution as n approaches infinity. This is called Wilks' theorem. It's a very complicated theorem. I'm not going to go anywhere near it, but if you want to read about how the theorem is proved, you can read layman's text on testing statistical hypotheses, but I can warn you that I couldn't understand the proof. Okay, so we just take it for granted. Okay, so here we go. So we have the likelihood ratio test now defined in terms of the log likelihood difference, right? And notice that instead of writing -2 times the log likelihood for theta 0 minus the log likelihood of theta 1, I could remove this negation sign by just saying 2 times the log likelihood of theta 1 minus the log likelihood of theta 0, right? So I can just rewrite this in without the negation. So you should not get confused. It's the same thing. So sometimes when you see the likelihood ratio test, you'll see it presented as an equation 38, and sometimes you'll see it presented as an equation 36. Okay, so don't be confused about that. It's just manipulating the negation. Okay, that's the negative sign. All right, so let's do a practical example now to see how the likelihood ratio test would work. So I'm going to generate some data y, and I'm generating it from a linear model where beta 0 is 10 and beta 1 is the slope is 2, right? This got ugly. Right, so I'm fitting a model where beta 0 is 10 and beta 1 is 2. I've got x and epsilon here. So I'm generating epsilons from normal distribution with standard deviation 0 and mean 0 and standard deviation 10, right? So I'm generating some fake data here. So this is your first simulated data set. We are going to go much further in this course when we are simulating repeated measures data, but this is a simulated data set that we're going to work with to see how the likelihood ratio test works out. So here's my data. I've got y, I know what my true parameters are, 10 and 2, right? And so if I look at the data, this is my x values, these are my y values. So if I just eyeball this data, maybe the linear model looks something like this, I don't know. So I can now fit a linear model with only an intercept. So this is my null hypothesis model, which really is saying that beta 1 is 0. That's my null hypothesis here, okay? And then I'm going to fit an alternative model where I'm assuming that there is a slope present. Okay, that's the full model that I'm going to have. So I've got a null model M0 and an alternative model M1. So what I'm going to do now is I'm going to compute the log likelihood of model 0, the log likelihood of model 1, take the differences between those two, and minus 2 times that tells me the difference in the log likelihoods, right? And that is 5.256. Okay, so now I'm going to compare this log likelihood that I've observed, this log likelihood difference that I've observed, I'm going to compare it with the critical value of a chi-squared distribution with 1 degree of freedom. Why 1 degree of freedom? Because there's only one extra parameter, the slope parameter, in the model M1, right? So the chi-squared distribution with 1 degree of freedom looks something like this, and it has a critical value of 3.85 as is the critical point, such that the area to the right of it is 5%, right? So this is again like the rejection point in the t-test. If my observed difference in the log likelihoods lands in this rejection region, and it does, as you can see, then I will reject the null hypothesis, that there is no difference, that there is no effect of that beta 1 is 0, right? That was my null hypothesis. I would reject this now because I've got a larger difference in log likelihoods relative to the critical chi-squared value that I get when I compute it using the Q chi-squared function, right? Notice that I'm using the Q family of functions here for the chi-squared distribution. Remember I told you that for every standard distribution, R provides this Q, the D, P, Q and R family of functions. So I'm using the Q chi-squared function to compute the critical cutoff value for the chi-squared statistic, such that I can decide whether to reject a null or not. Okay, just like the t-test. I can also compute the p-value now, because if the chi-squared distribution for 1 degree of freedom looks like this, with 3.8 as the cutoff, and my observed difference in log likelihood is 5.256, something like this, let's say 5.256, I can compute the area under the curve here using the p chi-squared function. So I gave it as input the number 5.256. Degrees of freedom is again 1, and I'm computing the area under the curve to the right of that point. That's why lower tail is equal to false. Okay, and so this is my p-value. This is my p-value from the likelihood ratio test. Okay, so given a type 1 error of 0.05, I'm happy to reject the null here. Okay, fine. So this is what I just did. I compared it, and what we are doing here is that we are actually comparing two models, M0 and M1, and these models are actually nested. One is nested inside the other. What I mean is that the first model has this basic setup, and the second model, which I'm calling M1 has a superstructure in the sense that it has one extra parameter, right? So model M0 is nested inside M1, right? Now a situation where you wouldn't have any nesting is something like this. Extreme example, okay? So you could have a model where you've got the same data, and my model M0 could be beta 0 plus beta 1 x plus epsilon, and my model 1 could be y beta 0 plus beta 1 z, where z is some other variable. You know, so like this could be word length, this could be word length, this could be frequency, right? I could be looking at the effect of word length and frequency in two separate models with the same data, and I could be comparing those two models, you know, but that's not a nested model, right? Because there were different predictors in these models. So I'm only talking about these nested comparisons here. Okay, we are comparing one. Whenever we do our hypothesis tests, we will be doing these kind of nested model comparisons with a parameter present or absent. Okay, that's how we will do the tests always. Okay, so where are we now? Right, so now we come to the closely related concept of an analysis of variance now. So we can do the same kind of likelihood ratio test in the analysis of variance framework, and with the way that would work is that I would take the null model and the alternative model and push it through the ANOVA function, and what that will do is that it will give me a statistic called the F statistic, which also tells me whether I can reject the null hypothesis or not, right? That's basically the same logic all over again. And as you can see, the p-value also is shown in the ANOVA function, and because it's below 0.05, I can reject the null hypothesis that there is no effect of the predictor X. So I would then say that there's a significant effect of the predictor X on Y, right? So this F score that you're seeing here, 5.53, is actually the square of the t-value that you would get in a t-test that you would do with the linear model, right? So in the ANOVA, I can extract the F score, right? And if I take the square root of that, I get a value that is 2.352. But if I fit the model M1, the linear model M1, which one was that? Let me show you. This model here, when I fit this model and I print out the summary of that model, right? And I look at the coefficients table, and if I look at the t-value of the slope, it's exactly the same as the square root of the F. So there's actually a fundamental result in statistics that t squared is equal to F. So when you do the linear model test, that t-test that you're doing is actually going to be very similar or basically identical to the ANOVA. There are situations where it will not be the same number, and that will happen when you have imbalance in the data. But asymptotically, as the sample size goes to infinity, these tests are identical. Okay. So these things are discussed, these points are discussed in various textbooks. There's a famous introduction to generalized linear models textbook. I may even have it here. Let me see. So this textbook here, right? Introduction to Generalized Linear Models. This is the classic textbook by Dobson and Barnett. This is the 3rd edition, right? This book actually discusses a lot of the details of these issues that I'm quickly going through, right? The main point here, though, is that the t-test and the ANOVA really are giving you the same information. The t-test and the linear model are giving you the same information, right? And in fact, the likelihood ratio test and the ANOVA are also giving you the same information asymptotically. As the sample size goes to infinity, these are all the same thing, basically, okay? All right, so now I'm going to explain to you how the ANOVA comes about, okay? So sometimes people ask me this question. I generally try to hedge and avoid answering this question, but today I decided to do it, okay? So if you can survive the last 10 slides or so of this lecture, you will understand how what the payoff is of learning the matrix formulation of the linear model, because you can very quickly derive the analysis of variance without any drama, okay, once you know matrix algebra. So now you can see the power of mathematics in action, okay? So first of all, remember I drew that graphic for you guys. Remember that I had drawn this thing. I'm not going to go and try to find it again. I have the x beta and I have my y vector, right? And I said that I want to find this x beta hat, and I'm going to get this epsilon, which is going to be defined as y minus x beta hat. Remember, this was some time back when I showed the matrix formulation, right? So there's that thing here, the residual, okay, y minus x beta hat. So now what I'm going to do is that we're going to talk about the square of this term, right? So we're going to square the residuals. All right, just bear with me here. So once you've squared the residuals, we're going to define a new concept which is called deviance, capital D, and deviance will be defined as the sum of these squared deviances. So basically it's going to give you a measure of the square of the variability around the mean values. Okay, that's what the variance also does, by the way, right? The variance gives you the sum of the squared variances around the sample mean, right? So it's very similar to the variance concept, this deviance. And notice that in this definition I've got the squared deviances and then dividing by the standard deviation squared. So that means I'm normalizing the variance by dividing by normalizing the deviance by dividing it by the variance. Okay, so this is what the definition of the term deviance is. Okay, so once I've defined deviance like this, now I can just do the matrix algebra and work out all the details. Okay, so that's what I'm about to do now. So the first thing to notice here in this expression is that I've got a transpose here. So I'm going to unpack this transpose, and the way you would unpack the transpose is that if I have y minus x beta hat transpose, if I want to unpack it, I would have I would have y transpose minus, I will have to flip the x and beta hat, right? So beta hat transpose x transpose, right? So that's what's happened here, right? So I've opened out the transpose here, and now what I'm going to do is I'm going to multiply this entire term with this term using just standard algebra. This is just standard algebra, right? Remember, in algebra you have something like, let's see, let me remind you how this works. There's nothing dramatic happening here. So if I have something like a minus b and I multiply with c minus d, right, what's going to happen? I'm going to go ac minus ad minus bc plus bd, right? Something like that. I hope I got this right, but that's just standard stuff, right, that we do in algebra. So I'm going to do exactly the same thing in this calculation here. So I've got y transpose multiplied with this y transpose here multiplied with the first term y, that gives me y transpose y. Then I do y transpose multiplied with the second term minus x beta hat, that gives me y transpose minus y transpose x beta hat. And similarly I take the second term minus beta hat transpose x transpose multiplied with y, that gives me minus beta hat transpose x transpose y, plus I'm going to multiply this term with this term now, and that there are two negative signs, therefore I get a positive sign, and I end up with beta hat transpose x transpose multiplied with the second term x beta hat. Wow, that was quite a mouthful. So now we end up with expanding these terms, right? So now we're going to simplify them. Now one thing that we know from linear modeling theory, which I just showed you in part 1, was that beta hat is this term here, right? We had derived this earlier. Now if I pre-multiply both sides with the inverse, with the x transpose x, I'm going to wipe out this term, right? This term will get wiped out if I pre-multiply both sides with x transpose x. So that's what I've done here, and so I get this simplified. This term is what is left on the right hand side, right? So what this means is that in equation 41 we have this term here, right? Sorry, no, not this term. Let me just undo that. Right, so because we can let me see, x transpose y, yeah, right, so we're going to use the fact that x transpose y can be written as x transpose x beta hat. Okay, so equation 41, that is this one here, is going to be rewritten now as follows. We are going to replace this term x transpose x beta hat with x transpose y. So where is x transpose, where is x transpose x beta hat? X transpose x beta hat is over here, So I'm going to replace this one with X transpose Y, right? That's what's going to happen now, right? So that's what I've done now. I've replaced X transpose X beta hat with X transpose Y, right? This is what I've done here, right? And so what that does now is something pretty cool. Can you see what's happening? This simplifies the equation. This simplifies the equation because this term and this term are going to cancel out, right? Here we go. And once we do that, what I have is 1 over sigma squared multiplied with Y transpose Y minus Y transpose X beta hat. That's a much simpler equation. Okay. Now, one interesting thing to notice is that Y transpose X beta hat is a scalar. It's going to be 1 by 1. Let's find out why. Okay. So Y is an n by 1 matrix, right? Because if you remember in the Y X beta plus epsilon linear modeling framework, X was n by P matrix and beta was a P by 1 matrix, right? So if Y is an n by 1 matrix, and epsilon is n by 1, right? So if Y is an n by 1 matrix, Y transpose is going to be what? It's going to be 1 by n matrix. X is an n by P matrix, and beta hat is going to be a P by 1 matrix. So if I multiply a 1 by n matrix with an n by P matrix and then multiply that with a P by 1 matrix, I'm going to get a 1 by 1 matrix. That's a scalar. That's going to be a number. It's not going to be a matrix anymore. Okay. So we can basically now write here we can reverse this because that will also be a scalar, right? So we just rewrite these terms here, and now we've got a definition of deviance in terms of sigma squared, beta hat, X and Y. Okay. So let's say that we have a null hypothesis that beta, one of the betas is equal to some value beta 0. Let's say the slope is set to be 0 or something like that. And then we have an alternative hypothesis that slope has some other value. Okay. So let's assume that our null hypothesis model has q parameters, right? So remember that when I have a model like beta 0 plus epsilon, that's my null model, right? That has a certain number of parameters, and we'll say that they're q parameters. The other model that I will have one extra parameter, right? It'll have p parameters, and p will be larger than q. That's a stipulation that I'm making, that I'm going to have more parameters in the alternative model than in the null model. Okay, right. So we have a design matrix now that is specified for the null model, and then we have a design matrix that is specified for the alternative model, right? That's what I'm calling X sub 0 is the design matrix or the model matrix for the null model. X1 is the design or model matrix for the alternative model, right? Okay, so what we're going to do is we're going to compute the deviances for the null and the alternative model, right? Just look here. This is the definition for deviance. Once I know what my design matrix is, once I know what my y vector is, and I know my standard deviation, I can compute the deviance, right? So I compute the deviance under the two models. That means under the two design matrices, and I compute the difference in the deviance. That's the delta D again, right? So this should remind you of the likelihood ratio test, which was a difference in the log likelihoods. Now we are doing a difference in deviances, right? And so once I do these computations, I just work through the algebra of this, I end up with this term here. Okay, you can work it out. If you just do the algebra, you'll see that this term will cancel out, these two terms will cancel out, leaving us with these two guys. And if you rearrange the terms, remove the brackets and rearrange the terms, or shall I just do it? Let me just do this. Okay, maybe I'm going too fast here. Where is it? Let me erase all this. right? So what am I doing here? Take a look at this, right? So I'm going to simplify these terms here. This looks very scary, but actually it's not. So I've got y transpose y, and I've got minus beta 0 x0 transpose y, and now I'm opening brackets. Okay, so there's a brackets here. So if I remove the brackets, I've got y transpose y. There's a negative sign here and a negative sign here, so I'm going to end up with a positive sign, which is beta 1 hat x1 transpose y, right? So I've simplified, and so now I can see that these two guys will cancel out, and this is a negation, this is a negative term, this is a positive term. So if I move the positive term to the beginning, I end up with beta 1 hat x1 transpose y minus beta 0 hat x0 transpose y, right? So that's this term here, and so now I've got the difference in the deviances in terms of the two design matrices and the hypothesized betas, right? All right, so it turns out that there's a test statistic here as well, just like we had the chi-squared statistic, and before that we had the t statistic and so on, right? There is the f statistic which has the following distribution if the null hypothesis is true. So remember, delta d was something that we just calculated under the two models. The difference in the number of parameters is p minus q in the two models, right? N is the number of data points, and p is the number of parameters in the full model, right? And d1 is the deviance of the full model. Okay, so it just turns out that there is the distribution of this ratio of the delta d divided by p minus q to delta 1 divided by n minus p has an f distribution, which is again a probability density function, which looks something like this for different degrees of freedom. The f distribution takes two parameters, right? Which are I don't know, sometimes these are called df1 and df2 or something, right? And so these two parameters are the denominators in the numerator and denominator of this ratio here. Okay, so basically what we are getting here, let me erase all this again. What we are doing here is that just like we were computing the t statistic and the chi-squared statistic and all that stuff, we are computing a new statistic called the f statistic, which is the ratio of these two deviances divided by their differences in degrees of freedom. And this ratio happens to have a particular distribution asymptotically or under repeated sampling, right? So basically this distribution is this f distribution, so we can compare the observed f score with some theoretical cutoff point in this f distribution, and if our observed f score lands in the rejection region, we can reject the null hypothesis. It's the same logic all over again as the t-test and the likelihood ratio test and so on. So so let's do this in practice now. So we know how to compute delta d, right? That's this term here. I just derived that a few minutes ago, right? And we know that p minus q is whatever like the difference will be. I think it might be 1 or something in this case. And the denominator is just the deviance of the alternative model divided by n minus p, which is the number, p is the number of parameters in the model, n is the number of data points. Okay, so we compute these numbers, just do the matrix algebra, that's it, right? And once we do that, we get the f statistic, and then we either reject or don't reject based on whether we land outside the cutoff point or not. Now typically you will see in classical psychology textbooks, they will provide you with a table of sum of squares and the mean squares and so on. So what I've shown you here is how these sum of squares and mean squares translate, what they translate to in our matrix formulation. Okay, so in the matrix formulation, the numerator and the denominator, right, are what the psychologists call the mean squares, right, of the f statistic, right? And that's what is used to compute the f statistic. And the sum of squares are given in this column here. I won't walk you through the details, but the basic the beauty of this presentation is that we can very quickly derive the logic of the F statistic using this matrix formulation, and it shows you the power of the matrix formulation of the linear model. I hope that you can see that this gives you much faster access to the underlying theory than going through the long detailed derivations that you will often find in non-algebraic presentations. For example, there's a great textbook by Maxwell and Delaney, Designing Analysis, Designing Experiments and Analyzing Data, DEAD. Okay, that book is called DEAD, Designing Experiments and Analyzing Data. It's a beautiful textbook, Maxwell and Delaney, and this book actually derives the ANOVA using sums of squares and lots of algebraic derivations. None of this matrix algebra nonsense that I've shown you, but it's much more work, in my opinion, to get to that derivation than if you do it from the matrix algebra point of view. And in any case, it's good to see that you can derive the Maxwell and Delaney type of derivations. You can do them very quickly in the matrix format as well. Okay, so there are different ways of deriving the same F statistic, this thing here that I've just shown you. Okay, all right, so all this drama actually boils down to not much in practice, because the actual statistical test that you're going to do will just involve using the ANOVA function with the null model and the alternative model. So this is kind of anticlimactic now, because after all this hard work, all I'm telling you is that you need to define your null model, you need to define your alternative model, and the software will tell you what the observed F statistic, what this observed F statistic is, and it will compare it to the criterion for a F statistic with 1 degrees of freedom in the numerator and 9 degrees of freedom in the denominator. Okay, so it's comparing the critical value of this observed F statistic against this distribution. Okay, so let me see if I can do this quickly and show you how this works. Okay, so I hope I'm not going to embarrass myself now and get this wrong. So we're going to compute the p-value I think in the F distribution, where I have different degrees of freedom. Right, I have degrees of freedom 1 and 2, right? So I have degrees of freedom 1 for the numerator and 9 for the denominator. And what was my observed value? So I had observed F statistic. My observed F statistic is 5.53. And my reference distribution is an F distribution with 1 and 9 degrees of freedom. And what I want to know is the probability of getting 5.53 or something more extreme, right? So I'm going to use the QF function, 5.53 or something more extreme. That means lower tail equal to false, right? I want to know the probability of observing this value. Oops a daisy, what have I done wrong? Oh, sorry. I want the probability. I keep getting confused about Q and F. So I want the probability. Damn it, I'm just mistyping this every time. Right? And once I compute the probability, if I round it to, let's say, 2 digits, okay? Rounding this to 2 digits, or let's say 3 digits, let's say. 0.4043, that should be pretty much what I get from my test here. So I don't know why I got 0.047 here. It should have been 0.043. Am I doing something wrong here? My full model has 8 degrees of freedom. I'm sorry about that. So this should have been 8, I think, not 9. 0.047 should be exactly what I get from the model here. So my mistake was that I had the wrong degrees of freedom in my F statistic, and so I can reproduce this p-value by looking up the relevant F distribution for the relevant degrees of freedom. And the way I would report, sorry, this is wrong here. I should have written 8 here. So the way I would report this result in the paper, would be that my F statistic was 5.53 with a p-value of 0.047, which allows me to reject the null hypothesis that there is no effect of X on Y. Okay, so that's basically how this statistical test would work. Okay, so I think we are ready to rock and roll and start talking about more interesting things relating to contrast coding now, and to the linear mixed model, and then simulating data to understand power and other concepts in the linear model and the linear mixed model.